So what I'm going to be talking about today is general curvilinear motion, and this follows on from the first lecture, which looked at single dimensional motion, that is a particle traveling along a straight line. And so learning objectives, what happens when a particle is traveling along a curved path, and how do you describe position, velocity, and acceleration for these paths? And it's clear that things are going to be a bit different. So if I look at what's happening here, I have a path which is defined here and I've just drawn a handwritten arrow on there so you can see it. That tells you where the particle is with respect to the origin. So the particle's here and it's traveling along this curved path, and it's probably, I'm going to say it's going to be traveling along this direction. And so the position and direction with respect to the origin are going to be defined by this function. R is equal to R as a function of time, and R is just going to be this right here, which is the distance from the center. Particle travels to a new position, and that's going to be R prime. So again, as before, I'm going to use this as a way of defining displacement. And by defining displacement, I can define it with respect to delta r, which is the difference in the position of the vector r and the vector r prime. So r prime minus r, and you can see that in the figure right there. And the only other thing is that instead of a vector, I was looking, say, at a scalar quantity, it would be the displacement along this path. So this is not a great drawing, but it doesn't go directly to the path, and I mean, I'm not showing that the particle is small, but this is just to give you an idea. In terms of curvilinear kinematics for velocity, again, r is defined here, and now I've got this displacement relationship which I know about, and that's v equals delta r over delta t. And at the limit, delta t approaches 0, delta r over delta t equals dr dt. As dr gets smaller, it approaches the tangent of the curve, and so you've got this right here. It's nice, goes off into up and tangent to the curve, and it continues well. The average velocity or speed is just going to be the displacement of the particle along that path over some delta t, and that's kind of useful for references when we talk about speed. dr is tangent to the curve, and the direction of v is also tangent to the curve. So as you get smaller and smaller values, you get to smaller and smaller limits. If you want the instantaneous speed, you do the same thing as before, which is you take the limit as delta t approaches 0 of delta s over delta t, and you get ds over dt. Problem is acceleration. Acceleration does not act tangentially to the curve. So instead, I can take my velocity at a couple points. I know it's tangential to the curve, and you can see that in these two cases, r and r prime. V prime and v are both defined there. So if I take all of the vectors as I go from v to v prime and maybe a couple more points along here, I'll have vectors that curve like this. And as they curve, these are going to create something called a hodograph. And the hodograph is the curve that defines the heads of all of the velocity vectors. And I can use that and say that curve is the line, or is the curve to which the acceleration is tangential. And so you can see there, I've drawn a tangential to it. But one of the things you'll notice is that when I replace that into my original field, it is not tangential to the path. So the acceleration average is delta v over delta t. Acceleration at the limit is dv dt, which is what you kind of expect. And the second derivative position with respect to time. So in terms of what has been done here, we've defined position, velocity, and acceleration for curvilinear motion. And one of the toughest things to remember in this course is velocity is tangential to the path, acceleration is tangential to the hodograph. And you don't really use the hodograph too much, but the more important thing is don't assume that the acceleration is going to have any relation to the geometric path defined by the motion.